will be reflected to the antenna. By this means we can know the structure or layer or objects in the underground. We have in the deep space, we have explored both the moon, the near side by Chang'e 3. It is the first mission to explore the planet shallow structures, and Chang'e 4 is on the far side of the moon. Tianmen 1 is in the Utopia Planitia on the Mars, and the Perseverance is in J0 crater. So we can see it's very popular in recent years for the ground penetrating radar GPR rover, and the main advantages is on its high resolution, although its detection is somewhat local region and have very shallow depths. Anyway, it can provide a very detailed profile of the subsurface. By contrast, the orbital GPR is deployed on the satellite. So this means it's very famous on its global range detection. However, its shortcoming is on deep. It can only has a very low resolution because the frequency is very low, and we have a very huge spherical spreading due to the too high the altitude over the ground. So anyway, we have more orbital GPR exploration or missions since the 1972. The Apollo lunar sound experiment is the first orbital radar for the planet. After that, we have the Marses. It's from the ESA, and Sharad is from NASA. These two payloads are still in operating. So we are now can obtain many new data each month or each year. So for the lunar sounder is from JAXA, from Japan. Or Tianmen 1 is from China. And for this year, the radar for icy moon exploration to the Jupiter has been launched. So we will expect a very more data obtained in future for planetary exploration by radar, both for orbital GPR or for rover GPR. Here, however, here is the typical picture profile of Mars. We can see that it has very low or relatively low signal to noise ratio, because we can see even before the first reflection of the ground, we still have many or strong noises there. So it's a great challenge to do some data processing of orbital radar to reveal the details of subsurface structures. Anyway, we are hoping to develop some new methods to deal with this problem. We know that for the moon or the Mars of any planet, because they experience a very long history of impacting, so there are many strong heterogeneity in the subsurfaces, especially for the vacuum cavity. Vacuum cavity is not so serious for the radar exploration. However, it will very much more serious for the seismic wave propagation. So anyway, for the GPR detection, we besides the strong heterogeneity of the subsurface structure, we also have many above surface reflections that can be called by artificials, because with the height of the rover could not be that low. It has to have a high enough height to make sure it will not be stopped by any obstacles. That means we have no shield to avoid the reflection from the above surface objects, such as the rocks or the topography. Our main aim is to detect the subsurface structure. However, the surface above surface reflection will dominate the energy of the profile. That means usually the most important or dominant energy is from the above surface objects. So we have to develop some new method to deal with such cases. Here is our model. Our target is to detect the signal from the reflectors. However, our input data or the data we can obtain is D. We denote it as D, and we can see the target reflection will be convoluted to the source time function. That means the impulse, because the impulse is not usually perfect, so it has some duration. Usually is not that short. It's very long. So the convolution of the source time function S to the target or the reflection would be also convoluted to the instrumental response. That means our antenna is not a full pass band. So that means the convolution of ITS, and also we will have the noise. Usually we have some different kinds of noise. That means this is the model, the noise plus the convolution between the instrument response, the target, and the source time function. So our task is to extract the T as many as we can from data D. So for the better for the hardware, people will say we can design a better instrument. However, after the payload had been launched, we have no chance to improve the hardware anymore. Also, for the operation, due to the limitation of the extreme condition of our planet, we can't perform as more observations, because the rover it's very difficult to plan the route of the rover. That means we can usually have one chance to observe some target. However, on the ground, on the Earth, we can usually observe for many times to make sure the data will be as clear as possible. However, on the planet, it's not possible. Finally, when the payload have been the payload or the mission finished, we have only one chance to do our homework. That means we have to develop new algorithm to make sure the data can be well mined or well developed. So next, move to the extracting weak signals. Let's see how can we extracting weak signals from the strong noise background. Basically, we have people have developed many kinds of different methods to extract noise from random background noise. We can it's not the full family of all methods, but anyway, this is only from the seismic exploration field. It's mainly using the artificial exploration by emit ground vibration and to detect the oil and gas underground. Anyway, in this field, people develop many different methods. They can be called as the prediction method, medium filtering method, decomposition or rank reduced method, or sparse transformation method, such as we can use Radon, wavelet transform, and FFT, or GABA, or windowed FFT. Even we can use machine learning. However, all of these methods are somewhat not effective to deal with that strong background noise of planetary radar data, as shown below. The challenge is that, therefore, the challenge in front of us is to to develop extract weak signal below strong background noise. Also, we know that the sensitivity is also limited because any payload will have a limitation on its sensitivity. So after the payload had been launched, we can't improve the limit. So anyway, we still have some chances to detect the very weak signal that is above the sensitivity limit. This is our main points. So for any kinds of method of denoising, we can obtain a denoiser profile as this, and the residue is the noise background. However, we can see that any method. However, we can see that there are some similarity. We can see that we have a 3 hyperbola here, and we have a 3 hyperbolic shapes similar to this. That means we have some signal leakage in the background noise. So if we hope we can extract this one, we can improve the signal to noise ratio in the denoised data. So people are still trying to develop new method. I think one of the most famous method that is very effective is from Yang Chen from CG in Geophysics or GGI. This method is called as local or signalization method. That means it will to compare the similarity between the denoise method, denoise profile to the noise profile. If they can see some similarity, then this part will be fetched or extract from the background noise, and this part will be added to the denoised part. In that means we can see the noise ratio is slightly improved, and the noise is much more like noise, and the similar signal has been moved or removed to the signal profile. After that, we can see the denoised profile has less similarity with the noise. We can see it's almost homogeneous. However, we can still see very tiny hyperbola here. That means we still have some leakage in the background. How to extract this signal is very, very challenging, I think. So we are developing some method to extract such very, very or extremely weak signal, even if they are visible or can be detected by the, as I mentioned, if they are above the sensitivity limit. So we develop new method. That means we can perform here. Sorry, this model is due to 3 objects or scattering points. We have 1, 2, 3 in model domain. Here is the data domain, observed data. Here, if the model, we have 3 scattering points. So their profile is 3 hyperbolas. So if we perform a migration, that means we collapse all the hyperbolas into their original points. That means we can obtain a very concentrated signal there that is corresponding to the reflector. So by that means we can see many crosses. Anyway, the center of this is the scattering points or the objects. This is another, and this is the third. We can see all the objects has been detected clearly after perform migration. Similarly, or at the same time, we also perform the migration to the noise background. Usually, we do not perform any data processing on the noise profile. In our case, we do this to parallel to the denoised profile and the noise profile. We can see that there are some similarity on the scattering points. So that means we can extract more signal in the migration domain. After migration, we can see the similarity is dominant. So this part of signal can be extracted by local the similar method as this local signalization method. So after that, we can say, oh, we have extracted very tiny signal by this. So these 3 points are signal from the reflectors, even though they may be very tiny or very weak or very for each trace. On this trace, the signal to noise ratio is very, very low, and also in many other traces, it's the same cases. However, after migration, the hyperbola has been concentrated or focused to the scattering points. That means the signal in these trace is very, very larger, much larger than before. So therefore, we can use the local or signalization to improve the signal to noise ratio here. And this part can be demigrated. That means we perform migration to the denoised data, and we perform the demigration on this. We can obtain the hyperbola there. This part of signal can be added to the denoised data, and we can improve the signal of reflections. We can see now that local similarity is almost homogeneous compared with that. We still can pick up or extract weak signal more. Of course, people can develop new methods to improve the signal to noise ratio after our processing. There is another case we can see. Here is the orbital GPR profile. It's obtained by the SHARA data by NASA. It operates almost 20 years. However, that we can see this is the signal after the SAR, the SAR, after SAR processing. However, we cannot identify detailed structure in the A region and the B region. Although people claim that there are some reflectors there, but how about this? How about this? How about this? What's that? It's an artificial reflection or layers. It's difficult for people to identify or distinguish between artificial and reflex. Here we may see there are many tiny structures, layer structures. However, usually they are not so clear, and lateral continuity is not so good. So we still need to develop some new method to improve the signal to noise ratio of the orbital GPR data. Here is a new method developed by my PhD student. He's now a postdoctor in my group, and his background is in the computer science. However, he finally decided to join in the frontiers of planetary exploration, especially for the orbital radar processing. The first of his work is on the speed up the algorithm of PID. The PID method is very popular in image data processing, the pure image or natural image processing. It's called as a progressive image denoising. This method is very popular. It used stochastic and deterministic method to deal with the noise detection and the reduction. This method is very popular. However, when we directly use this method to the SHARA data, it doesn't work. So after the speed up of this method, Pengfang hoping to try to develop a new method to improve based on the PID. Finally, he got a very a non-traditional method because it's somewhat not so good, because people usually do not add the denoised method into the original profile or the input data. That will ruin the reflectors, at least to my imagination. But finally, to our surprise, this method works very, very well. And we can see his idea is based on the PID. We can see first, let's set over some iteration times and some local or vertical or horizontal pixels to make combination. After that, we can have a initial noise level estimation, and then we can do some vertical stacking of key axes. That means k equals 3. That means the 3 vertical adjacent vertical pixels will be added up. That means we will lose some vertical resolution. However, when the vertical resolution is not as good as we not that good, we have to kill some vertical resolutions. In this way, we can also to perform some lateral moving average among 3 or 2 pixels. After that, we can perform the PID processing using the initial noise level. After that, we can obtain the first denoised data. The main point or the key point of this method is to extract local maximum as a mask. That means we only leave the dominated peaks by removing all the residues. Only leaving the peaks are there, and we have a scale on it about 3 or to 5%, and then this part will be added to the original input data. After that, we will perform another round of iteration using a new or better level noise level estimation. By this method, if we iterate for 3 or 5 times, we can obtain the final result. So the key point is on adding a small percent of peak of the PID denoised result back to the input or the original data. Then the iterative can obtain with a much bigger SNR sigma. That will be great helpful to improve the signal to noise ratio. Here is the perfect data, and here is the data of the speckle noise directly copied from the Sierra data before the ground surface reflection. And we can see that after this is the input by adding B and C. For the input data, we use 3 methods to perform some numerical comparison. We can see that for the popular medium filtering method, it cannot improve the method, even though we use a 3 or 5 template. And for PID, it's popular in the image denoising method, the original method. We can see that the denoised result is not that good. However, for the new method, we call it a new method here, it can clearly reduce the reflection above the surface and to identify most of layers. Especially, it can separate the very tiny structures here very close to each other. Even though we mentioned, even though we have we may use some combination of adjacent vertical pixels or adjacent lateral pixels. Anyway, we can see the layer can be well extracted here. This is very important. People may see, you only show some nearly horizontal reflectors. How about the dipping or high slope reflectors? The one point to mention that because the orbital radar is the payload is far from the ground. That means it can only detect the nearly horizontal reflectors. For the two dipping angles, the reflectors, the orbital GPR cannot detect, is not able to observe the reflections from there. So that means our method is somewhat catering to the orbital GPR data. So here's some results comparison of local with some local details. Here's the regional A we saw in the original profile. We can see that here we can see somewhat not so clear reflectors. Maybe people even cannot counter how many layers here, how many layers are here. However, after processing, we can see that using the two vertical adjacent by combination of two vertical pixels together with the horizontal 3 pixels, we can see that we can clearly show the main structures. That means we can see, oh, we have 5 reflector or 6 or 3. Or anyway, we can 1, 2, 3, 4 or 4 or 5. Also, we can see there's no reflectors here and here. Let's show again. So that means we can also see some artifacts here, but we can say, oh, yes, there are some reflector there, even though their slope is about that high. And also we can see the clear surface, ground surface reflections can also be well retained. So we can see this method is good at keep the fine resolution both for horizontal and lateral. Also, it can well capture the tiny structure like in the very deep objects. So for another case, we can show this is the B region. We can see there's many tiny reflections here, but finally we know it's not literally continuous. After using our method, we can see that the above surface noise can be almost completely reduced. Also, we can see that the reflectors can be greatly improved, and the lateral continuity is also improved. So that means this method will be very helpful for geologists or geophysicists to improve their imagination or interpretation of the subsurface structures. That means we can obtain a more accurate geological process of the Mars or Moon. So people, just as we mentioned, we have the convolution between the reflectivity and the wavelet, and here we omit the instrument response due to this model, and we only keep the noise, reflectivity, and the wavelet or source time function. We can see that if here is a model, we have many layers, and we have the reflectivity here. Both can be positive or negative, positive, negative. With the impulse of the short time function is somewhat wavelet. After convolution between these two, we can obtain a radiogram. But in the radiogram, it's very difficult to identify the accurate position of the layer. We can see that, oh, we can see some peaks, local peaks, but we can't make sure it's some of reflector corresponding to real subsurface layers or boundaries. So our aim is to deconvolute this source time function from the data to make sure we can see as clear or as close as possible to the reflectivity that will improve the vertical resolution. That is very important for any GPR data exploration. So the basic idea is to use the deterministic decon that it's with a sparse constraint. That means here is the weight, and here is the reflector, and here is the data. After that, we use the model. The model is considered as the sparse. That means we have only several layers. So after that, we use the minimum normal as norm as our constraint. Here is the 2 norm. After that, we can obtain a very sharp reflection on each layer boundary. That means we can deconvolve the theoretical wavelet. Thus, we can improve the vertical resolution. So here's the data. We can see the original reflection is like, here is a numerical simulation. The black line is the original reflection here, and here is the reconstructed waveform. That means after we obtain the reflectivity, we can also convolute to the wavelet. After that, we can reconstruct the waveform. After that, we can they are the same. That means the convolution or deconvolution is accurate. In the deconvoluted result, we can see here is some theoretical. The red bar are the theoretical reflectivity, and the dashed line is the deconvoluted reflectivity. We can see generally from the surface, the subsurface layers are what can be well recovered, although we may have some error or some artifacts. Anyway, this profile is much more easier to be identified to identify the subsurface structures compared with the original layer. We can see it's easy to identify, and this too. However, for this signal, the wiggle is do not show any dominant reflector. Here we can see, we have several, although we may have some artifacts, small artifacts there. The problem is on that for the later reflection, our current method may have some artifacts. So people, if people are using our method, please please note that for the deeper reflections, maybe have some errors or artificials. So here is the north polar cap of the Mars. We can see there are some icy blocks, icy layers. We can see the shapes of the North Polar Cap, and we selected this region because this region here is a local zoom in. We can see this region has a very flat topography. That means we can have less artificial from above surface reflection. So we can see that this is the original Sharad radiogram. We can see, here there are some reflectors, very clear. People will feel happy. However, the total number of the layers is limited. Also, we may see the vertical resolution is very low. That means we can count 1, 2, 3. We can see some positive and negative reflectivity. However, after using the deconvolution, we can see the results. The layer can be clearly identified. Well, and we can see the total number here would be doubled to the original profile. That means we can pick up the very tiny reflectivity, and those who are mixed or convoluted into each other, that can be separated by our deconvolution. So also we can see the horizontal or lateral continuity can also be improved. We can see after that we can see much more thin layers. Of course, we can also see some deep layers. As mentioned before, there may be some artifacts here. So please note this profile. However, for the early arrivals, it will be much more attractive to be interpreted as the geological reflections. Next, let's move to the wave field separation. Both on the Mars and the Moon, we have many crater. So it's a typical model. The typical model of the Moon of shallow structure is the buried crater model. Here's the buried crater, and here's the regolith over it. After we detect using both rover radar or the orbital radar, GPR radar, we can see such a profile. That means for such a shape, it can be mapped into such a kind of shape. That means it's merely due to the observation is too close to the ground surface, and we can have a triple arrival. So the migration is to decouple these two complicated shapes back into the reflectors. So the migration is very important to obtain the true reflectivity and the true shape or buried depth of the subsurface objects. So however, we have some challenge on this because this method is originally developed by seismic exploration for oil and field exploration. However, in that field, they have many redundant data because they use multi-offset. However, for the GPR detection, we usually have only one offset. That means the emission and the emission and the receiver are close to each other, and it can only have one. If we have one impulse emitted, however, we can only have one receiver. Usually, we have only one or two antenna to receive the reflections. That means we can't use the traditional method developed for extracting reflections or scatterings developed by oil and field method using the seismic exploration. So for GPR detection, we have to develop some new method. And people Sergey Formal developed such kind of method in 2007. The basic idea is to perform a plane wave deconstruction. That means the plane wave, the near the horizontal, can be regarded as the reflections. However, the curved or the hyperbolas can be regarded as a scattering. In that method, these two can be separated by this method, and we can using the scattering the waves, we can know with the variation of offset, we can have a hyperbola. If we are using a true or accurate model, we can make sure the hyperbolas can be focused. That means we can have a point from the reflector. So by tuning the model, we can obtain a very good estimation of the model. After that, we can transform this model into the velocity model, and then we can use the migration using the traditional migration by velocity method. Of course, the velocity can be convoluted or can be transformed from the relative permittivity of the rocks over under the light speed. However, we can see that the input data at the left panel, and the middle is the reflection separated from the scattering on the right panel. We can see that here is somewhat hyperbolas or curved shapes. However, for this part, we can see it's almost the same to the input data. That means the scattering we extracted is very tiny or very weak. It's very not so good for the helpful for the data processing when we are performing a numerical performing velocity analysis to build up the model. So we propose a new method to try to separate the reflection and the scattering. Our method is based on the basic idea that people will is one of a quite different method. This method is some kind of new style. That means usually if we are hoping to separate the signal to noise in the frequency domain or other domain, here is the model of the filtering method, but that means the low pass and the high pass method. However, we can see that for the low pass or high pass filtering, we have to set up a boundary here. The boundary should not be too sharp. It should be smooth between the signal and the noise. Otherwise, we will introduce some dips phenomena that is strong artifacts. So people have to set a range of this. So after that, the signal would be, if this is too left, then the signal will be ruined. If the signal is too close to the right side, the noise will be left into the signal profile. So we have a difficulty in select or set up a good boundary here. So this is the main drawback of all the transform waveform, traditional waveform separation methods. So basically, we transform the data into some domain, and we suppress the unwanted parts, and then we de-transform back to the original domain. By this method, attention band is needed and not easy to set or no way. So we propose to separate wave field during the migration and demigration. As mentioned before, we perform migration to the input data, and then we can make the image of some of the image of the data. In the migration domain, we can perform. People will say, "Oh, let's perform some attenuation." No any performance, no any action needed in the migration domain. After that, we directly perform the demigration back to the original domain. By this method, we can gradually reduce the random noise. People will say, "Oh, it doesn't work because you do anything in the migration domain." Yes, this is true, because we are using a kind of method that's very particular. It's based on a one-wave equation. It's a kind of some kind of wave propagation can only propagate in a given direction. So away from the given direction, the wave field can be gradually or naturally reduced during the migration and the demigration. So that means we smartly use their performance to be taken as a new filtering. So that meant that this is very important. Although the computational cost is relatively high, but it's worth that we can keep more signal and or remove more noise. So here's the propagation range in the wave number domain. Here's the ambient region. That means wave field in this region will be reduced or attenuated gradually. So the only thing we need to do is to set a proper velocity. The velocity, if the velocity here, we can see we set a proper velocity here to make sure this part is in the propagation region, and this part will be in the left. This part will be attenuated. So we can test different velocity to select the best parameter. We can see that for the signal here, layer 1 and layer 2, after using this method of propagation using migration, here is the traditional method. We can see many artifacts in the. However, to our method, we have no artifacts, and these two layers can be separated very well. However, for traditional method, they have many artifacts. In our method, they can be separated accurately. The most important property of this method is on that it can separate the very closed two layers. However, traditional method is difficult to achieve this aim. So I really strongly recommend this method for any people who would like to develop new method. Here is the result. Here is the input. Here's the reflection extracted by PWD by circuit formal. It's a kind of traditional method. Here's the scattering they extracted. We can see these two are very close to each other. That means the residue, what that means the scattering is weak, and the residue here reflection is still visible. We can see here is the horizontal reflection. Here we can see some reflection there. However, our method will perform in migration domain. It looks like this. In that domain, after demigration, we can see the reflections can be very well retained in our method, and all scattering are separated into this domain, and this domain is only the reflection. Compared with traditional method, we can see is much stronger for the scattering. However, we can know that for the head of the hyperbola, it will have be somewhat attenuated. Anyway, this method has also the similar effects. So in future works, we hope to develop some method to deal with this problem. Anyway, our new method can separate the reflection and the scattering waves better than traditional method to make the almost no visible residue in both profiles. Finally, I will move to some numerical. Oh, time is up. Hi. What's the time of?
It's okay. It's you can continue
Okay.
to. Yeah.
Sorry to explain that much details. Here we'll go through some example. Here is we know that the Chang'e 4 mission landed on the von Karman crater. It's the first lander on the far side of the moon. So people will hope to know the subsurface structure first. We can see that here is the crater. We can see even for this crater and a lot of craters. So we can see for this crater it's a Finsen crater or Leibniz crater. Anyway, this Leibniz is a Finsen crater, and we can see that the crater bottom is somewhat flat. Why? Because the crater will generate a downward shape of the shape. However, we can see it's a general flat. So what there there must be some feeding materials such as water or volcano or the basaltic magma. So, but we can see on the surface only can see the regolith layer. We can't see the basaltic layer. So what's the total depth or general depth of the basaltic layer, and how many layers, how depth and how many layers? It's very difficult to determine if without the GPR detection or some other geophysical detections. So Chang'e 4 mission can perform the first detection on this. We can see here's the rover. There are two channels. The first is the high frequency channel. It's about the dominant frequency is about 500 million hertz, and it's under the bottom of the rover. These two, we can see that these two is the low frequency channel. One is the two antenna. One is can emit an impulse. The other can be taken as an antenna. These two channel can explore both this can explore the shallow structure, and this can explore the deeper structure. So we can by combination of these two, we can obtain a very good resolution of a greater the deeper reflections. Here is the signal obtained. We can see there are many re-vibration between the rover bottom and the ground. So it's very strong. And also we can see some artifacts here, and we can also some nearly flat artificials. This is due to the the background noise of the GPR data, GPR equipment, or the background noise of the Luna. That's none of the business of the subsurface structures. Anyway, we say we have clutter, noise, and signal, the plus of these three. So after using our method, we can see we can remove most of the clutters. We can obtain a noise plus signal. However, we can still see some strong random noise like here. So finally, we use the other kind of method we developed before. We can see almost a clear bottom here. That means we can denoise and to remove the clutter and to extract various signal and to make sure the structure below is as accurate as we can. Here is the low frequency GPR for the Chang'e 4 mission. We can see here is the original observation. We can see it's only a part and not the whole profile. Anyway, Here, this part can have has much less reflections. So we can construct a numerical simulation to make sure, oh, for the basaltic layer, it have less reflection. So that means we have two layers. Original layer is very thick, over 100 kilometer, 100 meter depth, and also after that we have some regolith and paleoregolith. After that, we have a new basalt filling. So that means we detect two layers of basaltic layer over beneath the 130 meter beneath the ground surface, and we can see that the numerical simulation result is quite continuous to the observation. So this is another exploration on the Mars from Zhurong. Also, we mentioned before, with the Perseverance also have a rover GPR data in the J0 crater. Here we only mentioned the Utopia Planitia by Zhurong rover. It's located here. We can see here's the rover is moving. We can see the antenna of the low frequency. These two are the high frequency channel of the radar, of the GPR radar. Here's the low frequency. Of course, we have this antenna is not in the screen. Anyway, these two are generally follow the payloads from the Chang'e 4 mission. So we can see here is generally very flat. People will see here's in ancient days there is a ocean here. However, if is there any water still today over under the ground surface? There's no is there any water or not? We do not know. So the radar may reveal such kind of observations. So, however, unfortunately, the original data is not that clear. Almost all signal here are clutter and noise. We cannot see any visible signal. So after perform the data processing, we can see something in the 40 meter depth is relatively good. However, for this signal, it's almost artifacts. After to reduce the random noise, we can see some signal can be extracted from this part. That means we can see from 40 meter to 80 meters. This is the first exploration on that depth on Mars, because we know that the comparable data, the depth of Perseverance radar data is only reported is only 15 meter. Here we can see the 80 meter. That means we can see two layers generally, or not. It's not the traditional layer. It's a two somewhat a layer, not layer exactly layer, because layer usually means the reflector. Here we can see two suit of reflectors. This suit is have very weak reflection, and this suit is has a stronger reflection. So also we perform numerical simulation to compare the synthetic data and the observation. We can see we can recover the general pattern in observation. So we mean our model means that we have two suitable layers. For the upper suit, we have a smaller reflector or smaller rocky blocks, and for this one we have a much bigger or boulders in it. So by this way, we can explain maybe the Mars has experienced floods in ancient days. So this is the somewhat sedimentary structure due to the floods. So we can also see that this is only the vertical layer that we can see 3 layers. However, for the horizontal or lateral variation, we can see using the numerical spectrum analysis, we can see there are some local region that can have a much lower frequency That means the green region. We can see this we interpreted them as the polygon wedge, because when the rover is moving on the ground, we can see the edge here, or the polygon terrain here. So the diameter of all the edge thickness is about 25 meter, and the diameter is about 70. So we generally observed 16 edges, and it's buried under 35 meters. So we didn't see clear bottom of this structure. Anyway, this kind of polygon is popular on the ground surface, because for the E, D, and the C, CDE is corresponds to this. Oh, sorry, CDE. We can see around the Zhurong rover landing site, there are many places on above surface have similar polygon terrain or polygon structures. Although some of this has been ruined by the latest deposition. This kind of edge or polygon terrain is none of the business to the above structures. That means it's a real reflection from the subsurfaces. So we can also perform the edge detection on the figure. We can see the local zoom in. We can see, oh, there are many blocky there. We can count their number, and we can evaluate their diameter and to make some evaluation. And finally, we see, oh, the diameter and the edge thickness. So finally, we interpret it as we have 4 stages. First, for A, it experienced a thermal contraction cracking on the surface in the ancient days. After that, the cracks were infilled by water, ice, or soil materials. Then the polygon stopped, and the wedges were infilled by soil and sands or rocky materials. Finally, the surface had been buried by the deposits. This is maybe the great implication of this research is on that we have a clear reflection here in the 30 beneath the 30 meters. That means the Mars may experience a high obliquity in history in ancient days. I have to go through the future works quickly. We know that previous works are all using the GPR data, both for rover and the orbital. However, we know that the interior structure of the planet may have a spherical structure, the mantle, crust, and the core or inner core. For this aim, Apollo has deployed many seismometers, and the astronaut will deploy 1 seismometer in each mission, and finally they construct a very good aperture for seismic observation. However, due to the limitation of in the Apollo era, the seismometer performance is not that good. So finally, the detailed structure of the moon, even for the core or crust, is not well determined until now. So why this? We can see on the Earth, for the earthquake, we have a clear P and S arrival and a surface arrival, and even for the Koda waves, it's very clear. However, for the moon, we can see the general process is somewhat always Koda waves. There's no clear P, no clear S, and surface wave. So this is mainly due to the boulder regolith cavity, especially for vacuum cavities. They will strongly influence the propagation wave of propagation of seismic waves. That means for lateral model, we can have a clear PS. However, for the scatter model, the PS will not that clear. So how to deal with the scattering wave of Koda waves is very important for the detection of seismicity and for the interior spherical structure of the moon. Of course, we have limitation due to the seismometer, the narrow frequency broadband, and the low sensitivity. And also we have a limited number of events with the small magnitude. So in future, or in Chang'e 7, provide such a chance to observe the interior structure of the moon by deploying a seismometer there. It will be automatically deployed and with auto leveling, and it will launch in September 2026, and around the south pole of the moon. It will work more than 8 years, and will work together with the Chang'e 8 seismometer that is 100 kilometers away from Chang'e 7. So the Chang'e 7, fortunately, we have a chance to use GPR and the seismograph deployment simultaneously. That means this is the first time the GPR the GPR and the seismograph perform observation together. So the Chang'e 7 GPR will provide a good constraint on the shallow structure, and then the moonquakes from, especially for the weak signal from the core, would be greatly improved. So that means that it's helpful to constrain the shallow model. So we will stop in the conclusion here and here. Thank you.
Yeah, thank you very much. Very nice talk, Professor Zhang.
Sorry for my delay.
It's okay. We still have time. So, any question from audience? You can raise your hand. So there's one question from the chat box. So she's asking about the what is the clutter in the Utah 2 GPR image.
Yes, it's a good question. The clutter, sorry, here maybe a clutter. Yes, the clutter. There are many regions of the clutter. Maybe due to the surface reflection. That means we have many rocks on the surface. However, the contrast of permittivity between the air and the rock is very much higher than those of the contrast of beneath the ground surface. So that means the reflection directly from reflected the electric magnetic wave field are directly reflects from the rocks above surface. Their energy is very strong, so that's one of the region of the clutter. And also we have a topography and even the even other, maybe the whale of the whale, the roller whale will also have some reflections, and will have some towards different direction that will also introduce some clutter or artifacts. So these kind of things is difficult to be determined. So we can only to do some data processing to remove them. We only know that there are some artifacts, and their typical characteristic is on their strong energy. So we can remove them by data processing.
Thank you. Yeah, so I have another question. Yeah, what is the benefit of the rover GPR if we compare to the orbital GPR?
Yes.
Can we get a higher accuracy?
Yes. Here we can see here's the clutter region due to the reflect. If it's the ground surface is absolutely flat, there's no such kind of clutters. And if there's no wheel or no wheels for the rover, we can also have not this kind of clutters. However, we have to have wheels of the rover. We have many topography and ground surface reflectors. So the main advantages of the rover, although it can only detect a very limited range, because the rover can only travel within a small range, and it can only detect very narrow range of under the ground surface. However, it has a very high resolution because its frequency is very high. Usually, as mentioned above, for the Chang'e 4 mission, the GPR dominant frequency is about 500 million hertz, and for the high frequency and for the low frequency, it's still 50 million hertz. However, compared to for the orbital radar, it's only maybe 10 million hertz. It's far from the far from that of the rover GPR, because the low frequency GPR can propagate far away on the orbit on the satellites and their attenuation is also very much weaker than the high frequency radar wave. So the advantage is have a much big coverage of the planet. However, it can have a much lower resolution. As we mentioned, it can only detect a reflector, something like. Let's show you the resolution here for each layer is about over 10 meter. However, for Chang'e 4 mission, we can see several centimeter.
Thank you. So,
thank you.
Yeah, another question is if we have a orbital GPR, so how, if there's a surface topography, so how can we just remove the effect of the surface reflection?
Yes, it's a main topic for the orbital radar, GPR radar, because we can see that here, we can see something here. Yeah. Here, the reflection of this kind of reflection is mainly from the surface, not due to the not associated with any subsurface reflection. So this kind of things must be reduced or be identified first. Otherwise, we will misinterpret the results. So we know that when the rover is flying over the ground, we can see far away, not just under the satellite. We can see a very wider range of the on the surface. If the surface is not flat, the topographic reflection from faraway mountains will come into the profile, and we can see there are clutters. There are some kind of clutters. This kind of clutters can be simulated or can be simulated by accurate topographic model. That means we can, if we construct such a model, we can see such a kind of clutter. That means we can know, it's a kind of clutter. We can dismiss or we can regard this. However, if people can develop some method, we can even remove them digitally from the profile. That means we can leave more signals there, because some reflections can be buried under such kind of clutters. So do not only recognize they are clutters, we also need to develop some new method to deal with the weak signal buried under the clutters.
Yeah, thank you very much.
Thank you.
So, any question from audience?
Hello, can you hear me?
Yes.
Yeah, I have one question. So, is there other mission to land in the equator at the Mars, maybe near the inside? Because we know the inside is try to detect the Mars earthquake, right? So
yes.
So if there's any other plan try to compare with the inside data, or?
Yes. Basically, for the Marses from ESA and Sarah, these two payloads are still in operation. So this kind of these two orbital GPR can provide many valuable data over the InSight landing site. But however, due to the limitation of their resolution, people do not see clear reflection from the InSight landing data. Also from the Zhurong rover, we can see, as mentioned, for Zhurong rover we also have some. Sorry. Yes, here. For here, the insight is here, and the Zhurong is here. The perseverance. We have explored the Marses and shared the GPR data, but we can't see clear reflection above the 100-meter depth. So that means no clear visible reflectors. So we have to use the rover radar data. In future, maybe some new payload or some new missions can be sent to Mars to explore more detailed structure. But in maybe recent the nearest 10 years, we have maybe no such kind of plans, both from China and from many other countries. I will show you. Yeah, I will show you. There's a recent work on the radar for icy moon exploration to Jupiter. So this is still on his way flying to the planet, to the satellites of the moon of the Jupiter. So in several years, it can obtain new data of the icy moon of the Jupiter. So for the Tianwen-1 mission, the data is still in processing, and we can't see any reflections. Anyway, it's still running around the of the Mars. So basically these two is active, and the Tianwen-1 is active. It's on his this one is on its way. Also, we have active detecting for Chang'e 4 mission. Although its running speed is very slow, but anyway, it's still working. Each day or each month, it will provide new data from the far side of the moon, and the Perseverance is still working. So people or students could deploy the older data or new data from Chang'e 4, Perseverance, Mars is Sierra, Tianwen-1, and this one in future.
Okay, thanks for your explanation.
Okay, thank you.
Yeah, thank you very much. Yeah, so if there's no question from audience, so maybe we can end this talk here. So thank you very much, Professor Zhang. Thank you.
Thank you.
Yeah, very nice talk.
It's a new era for the deep space exploration,
Yes.
and I think young students can, how to say, make efforts or devote yourself into such a field. You're welcome. Thank you.
Yeah, thank you very much.
Thank you.
So bye-bye.
Bye-bye.